solid, liquid, and gas. Okay. Are we okay with these states of matter? All right. So we talked last time, how do we know what we know? How do we know what we know, and how do we know it's true? So this is kind of an example of how we know that. So first of all, let's talk about solids. If we look on the microscopic level, we zoom in way down deep, and let's say we can see atoms. We can't, but let's say we could. What would solid matter look like? Go ahead.
They would be bunched together.
Yeah.
Nothing in between.
Okay. Did we just get that from the book, or did someone tell us, or how do we know that? So that's what the book says. So if we have something like this, right? These little circles that I've drawn are atoms, so to say, okay? And I know that's not what an atom looks like, but we'll just be with me here. Okay, so they're all bunched together. That's trying to make a cube, right? Okay, we got a cube, and they're all bunched together. So they're close. How do we know that's the way that it is? We can't see it. We take a block of copper, let's say, and we stick it in this container that fits this block perfectly. And then we get another, so we stick this block inside a hole that fits it perfectly, and then we get a plunger that's square, and we push it straight down, right? Right on top of this. What's going to happen? It's going to stop, right? And we know this happens. Now, if we don't have a hole, if this isn't in a hole and we push it, it might squish it, right? But if we keep it in that same shape and we push down, can we compress those atoms together? Or that material together? We can't. And we know this. We've tested it. Now, there are different solids that have different properties, and they're not quite as dense, or right? But still, you cannot compress them. You might be able to, I don't know for sure. I didn't test on all materials, but you just cannot compress them. And that's how we know it looks something like that. You with me? Okay. What does liquid look like? Well, they're not as close together. But they flow past one another, right? How do we know that? We know liquid flows, right? So this cannot flow. Oops. This cannot flow. They're stuck together, right? Or they're too close. So it flows. And what about gas? There's a lot of gas in here, right? Called air. Can we take all this gas and push it into a little tank? Yeah, we can compress it together. So how must it look? If we look at the atoms, what must it look like? Yeah, spaced farther apart. And they can go any which way, right? At random. They also flow, but far apart. Good? So even though we can't see it, we have a good understanding of what it might look like. Good? On the microscopic level. Okay, another thing that we should know about solid liquids and gases is solids have a definite shape and volume. Now, I'm not saying you can't change its shape, but can you change its volume? If you have a pound of lead, can you change its volume? You cannot, right? You can change its shape, but once it's in that shape, it stays in that shape until you do something, right? So it has a definite shape, definite volume. Are you okay with that? And liquids, what about its definite shape, definite volume, indefinite shape, indefinite volume? What do you think?
Shape for sure.
Indefinite shape, but definite volume, right? Does that make sense? You can put it in a tall glass cup or a short, wide cup, right? So definite volume, but not definite shape. Okay? Then gas is no definite anything, right? Take all this gas, it's the shape of a cube right now. Well, it can go out into the atmosphere and be whatever. You can put it in a container and be whatever the shape that container is. And that volume of the container, change the volume. So not definite shape or volume. Again, just in words to saying why it looks the way that it looks, right? Any questions on states of matter? So kind of basic stuff. Let's talk about properties of matter next. We say basic, but again, we can't see it. How do we know it looks like that? Because of how it is, right? I'm just kidding, but okay. All right, there's two types of properties of matter. Let's talk about the first type is physical properties. So how do we know if a property is physical versus chemical? What makes it physical property?
We can detect it by our senses.
Good. We make observations. Or measurements. And we can kind of do that with chemical properties as well. But what makes it physical? It does not change the chemical composition, right? So we make observations or measurements without changing its composition. Am I writing large enough? You want me to write larger? Okay. All right, so let's give some examples of physical properties. We make observations, use our senses. We see this copper penny, and what do we see about it?
It's round.
It's round. So its shape, is that a physical property? We can see that it's round. Does that change what it is? No. Okay, so its shape. What else? Color, good.
Texture.
Texture. Size, maybe. What about the mass? We can't see it, but we can measure that, right? Mass, volume. Anything else? melting point, boiling point, density, good? Yeah.
Wouldn't the melting and the boiling point change the chemical composition?
Good question. Let's see. So if we put a thing of water on the stove and we boil it, let's say, we got to bring it 100 degrees Celsius, and it starts to boil. Now it turns into what? Gas, which is a state of matter, right? So that's also a physical property. Does it change what it is? Is it still water? It is. It's just now gas instead of liquid. So physical state of matter is also a physical property. Does that make sense?
What if there's like added material in it? Does it depend on what
So
mixture it is?
you can make a mixture of something,
Mm-hmm.
but now it just has two substances in it, and each of those substances have their own physical property, right?
Mm-hmm.
So even though you boil it or melt it, so for example, you melt copper and zinc together, and we make brass, right? Now, brass might have different properties than copper or zinc, but so if we melt it again, so copper or zinc, one of them has a higher or lower melting point, right? So if we melt it, we melt off the one with the lower melting point, and it comes off, and then we have pure copper again, or pure zinc, whatever one's higher, right? So whether it's a mixture of copper and zinc or separate, they still have their physical properties, and we did not change. When I say the composition, it still has copper atoms and zinc atoms. Great question, by the way. Copper atoms and zinc atoms. How do we know? Because they still have different physical properties. But you mix a silver-looking color with a orangish-brownish-looking color, and what does it make? A goldish-looking color, brass. And that's just the properties of how we see things, right? But it's still different atoms, and they're not bonded together chemically, if that makes sense. Good? Great question. I love that. And I don't know if I gave a great answer, but great question. Did I help?
Definitely.
Okay. All right, now there's two types of physical properties, or two classes of physical properties. We have intensive, we'll come back up to these, intensive properties, and extensive properties. Okay, one's in and one's X. In is like the innards, the guts, what it's made of. And so the intensive properties does not depend, that's good, does not depend on the amount of substance. Or of matter, I should say. Okay? And extensive does depend on the amount. Any questions on those two definitions? No?
When you say amount of matter, how is that measured?
It could be measured in volume, it could be measured in mass, it could be measured in even pounds, right? Just how much you have. It could even be measured in number of atoms, right? Great question. That make sense? Good? Okay. So let's circle all of these physical properties that are intensive. I'll circle in white because I wrote it in white, but okay. Or you can circle one and box others or whatever, okay? Or you can just label them, right? Should we label them? That might be easier for you to take notes. What do you think? Yeah? Okay. So shape. Intensive or extensive? So is all copper going to have the same shape? No, it does. So it does depend on how much you have. I guess you can have the same shape whether you have a lot or a little, but if you say, okay, what's the shape of copper? It must be round because that copper penny is round, right? Is all copper round? No, it doesn't have to be. So this is extensive. What about color? And the way I think about this, those are definitions, great definitions maybe, but I don't know, maybe we should give a better definition. Intensive is like what it's made of, inside. Inside, right, okay, and extensive is outside, the kind of what we see. But the shape, is that okay? What about color? Intensive, because no matter what, how much matter you have, how much copper you have, it's brownish oranges, right? Texture?
Intensive.
Yeah, intensive, right? And, well, you can shine up copper and you can have rough copper, but that one's kind of tricky. But let's see. I don't know. What do you think?
Well, if you take one piece of copper from one mine and one piece from another mine, they're gonna have the same, because they haven't been, like you said with the shining, that you have to shine them.
Uh-huh.
So therefore, you have to do something to them, instead of it just being the copper itself.
Okay. Yeah, all right. That sounds good. About size. Extensive, right? You have a ton of it versus an ounce of it, it's going to be different size. But it's still copper, right? So it's just the outside. Size doesn't tell us what it is. Mass. Extensive again. And volume. Also extensive, right? Melting point, boiling point. Intensive. Doesn't matter if you have an ounce or a ton, it's going to have the same melting point or boiling point. Density. it's also intensive, even though it's made of mass and volume, right? Mass over volume. Oh, but that's the ratio of mass and volume is fixed, right? Okay, so that's intensive. State of matter, solid, liquid, gas. Can copper be a gas? It can. All you have to do is get it hotter, right? At probably a really high temperature. Even though we haven't seen, hopefully we haven't seen gaseous copper. We breathe it in, right? Okay, bad news, right? Okay, but that's extensive property. Any questions with those? All right, so any questions about physical properties? We're going to need these when we talk about different classes of matter. So let's talk about chemical properties next. Not near as many chemical properties as physical properties. So let's just name a few, because that's all there are that I can think of. I don't know everything either, right? So we'll see. So if it's edible, how do we know something is edible? If you can swallow it? Digest it, right? If a baby swallows something plastic, what happens? We change his diaper and it's still there, right? It's not edible. And some things are, right? Okay? So edible is and how do you know if it's a chemical property? Well, it changes its composition as we measure or observe it, right? So it's basically the same definition of physical property, but it says we change the chemical composition. Good? If we eat food, we change the diaper, it's no longer food. We know that. Hopefully we can't taste it. We can smell it, right? It has different physical properties, so it's different material, different substance. Make sense? Sorry. Hopefully I didn't bring that. Okay, whatever. Okay. So what about if something reacts? For example, you throw plastic in water. Does plastic react with water? No, it'll just float on top, right? What happens if you throw sodium in water? Sodium chloride or salt will dissolve. But you guys know what sodium is? It's a metal. What happens if you throw sodium in water? It will sink a little bit, but it is highly reactive. You guys want to see this? Okay, not today. But when we talk about the periodic table, if I forget, you remind me. We'll take it outside and we'll do it. Okay? But it is highly reactive in water. Okay? So that's a chemical property of sodium. But most things don't react in water, right? Some things do, some things don't. Something is flammable, then, well, that means it burns, right? Okay. What else? If you can think of one that I'm not thinking of, let me know. Another one is oxidizes. What's another name for oxidize? Rust. Well, we know rust is not the same as iron, right? It's a different color, different texture even, right? It smells different, tastes different, has different physical properties. So we know it's something else. Well, what is oxidizing for silver called? Tarnishing, right? What's the color of copper when it oxidizes? Green. A lot of metals oxidize. Does gold? No, and that's why everybody loves it, right? It always stays beautiful. What?
Copper and aluminum don't oxidize.
Copper,
Aluminum, sorry.
aluminum, yeah, aluminum doesn't. What does it do? Because it almost seems like it can tarnish. Does it? Maybe not. Yeah, you might be right. You might be right. I know there's something with aluminum, so yeah, that's probably right. Anything? Can you think of anything else? Because I can't at the moment. So just a small list. There's probably more. Okay. Solubility.
Would that be part of like a reaction? Like
That is actually a physical property.
physical?
Because when you dissolve salt in water, or anything in water, it still has the properties of salt and it still has the properties of water, right? It tastes like salt and it tastes like water. And then you can separate them physically. That tells us it's a physical change, not a chemical change, right? Does that make sense?
Yeah.
Great question.
So would that be intensive then?
Yeah, intensive property. Yeah, question.
I mean, would dissolving be another one, just because, or would that go under reacts too?
So dissolving is also a physical process because, in fact, we will talk about it later. But if we put salt in water, so salt is sodium chloride, and you don't have to know this right now. We'll get into it. But since you brought it up, it's her fault. Okay. So sodium is a positive ion and chloride is a negative ion. And what happens when you throw it in water, it dissociates. We won't talk about why it does this. But then water will surround it. And I'm not going to draw the details. And once water surrounds it, that's how we know it's dissolved. Okay? But how is water surrounded? Because water, oops, wrong way. Water looks something like this. And this side of water is partially negative. And so they attract. It's just a physical attraction. Can you pull that back apart? Yeah, boil off the water, right? Okay. Maybe a little bit more detail than you want right now, but okay, we'll get there. Okay. So that's why it's a physical change, because we can separate it physically. Good?
So with chemical properties, it changes the chemical composition.
That's right. So, for example, we take sodium and we put it in water, and the sodium breaks up the water into these components. And this part right here is what makes it explosive or highly reactive in water, okay? Does that kind of make sense?
Yeah.
And maybe this is too much information too. We'll get there. Not today. We're not going to test on unit test 1, okay, exam 1.
Is that, sorry, I don't have a question.
No, you're good. Yeah, ask him.
Is that what you consider transmuting? Is that
Trans what?
transmuting? To change from one chemical composition to another? It's been
Oh,
such a long time since I took chemistry, I'm sorry.
I don't know that word.
Okay.
So it might be. Look it up and let me know. Sorry. No, that's good. Don't be sorry. Are we good there? All right. Let's classify the different types of matter. There's only 2 different classes, and each class has 2 different types. Okay, so there's 4 types, right? Okay, classification of matter. Okay, we got pure substances. And pure substance, there's really only 2 types of pure substance. Elements, you guys know what elements are? What? Gold is an example of an element. Sodium, oxygen, what?
Anything on the periodic table.
Perfect. Anything on the periodic table. So if it's on the periodic table, it's an element. That means it's a pure substance. Good? Well, yeah. So does oxygen have to be a pure substance? Or could it be with something else? It can be with something else. But then that brings us to compounds. Are the other type of pure substance. What are compounds? So let me give examples here. So elements is like gold. I'll just write it here. Gold, which is Au. And again, become familiar with the periodic table. If you're familiar with it, you're going to spend less time searching for stuff, right? Because like this one, gold, well, it doesn't even look like gold on the periodic table, right? Oxygen. Helium. And so on, right? There's 118. I was just trying to find good ones, right? Iron, silver, carbon, whatever. And what's a compound? Yeah.
Chemical composition?
It's a chemical composition of 2 or more elements. So 2 or more elements bonded together, not mixed, bonded together, like H2O, CO2, carbon dioxide, the stuff we breathe out, sugar, C12H22O11. This is the just sucrose, table sugar. Any compound, any chemical formula, right? That is a compound. Are we good? The other type of matter or class of matter is mixtures. So what's a mixture? Am I going too fast? No? 2 substances combined that can be separated. Is there only one P? Separated, yeah. By physical means. Questions on what makes it a mixture? So water is not a mixture. A lot of people say water is a mixture of hydrogen and oxygen. It's not. You cannot separate water physically, but you can chemically. You can do a chemical reaction and split them into hydrogen and oxygen. That make sense? Okay? There's 2 types of mixtures. Anybody read about these? Yeah, what are they?
Heterogeneous
Yeah, heterogeneous, homogeneous. I don't know the proper way to say it. Homogeneous sounds better, but it's not stuck in my mind. Okay. So, homogeneous. Let's do. And heterogeneous. Okay, homogeneous. Look at the prefixes. Homo, hetero. What does homo mean? Same. So it's a mixture. It doesn't mean it's the same substance, but it's the same composition throughout, right? Same throughout. We'll give some examples. And heterogeneous is different throughout. So let's give some examples here. So what about salt water? What do you think? Homogeneous, heterogeneous? What makes it homogeneous?
It's the same.
How do you know?
How you're pouring.
It looks the same. It even tastes the same, right? You ever go to the ocean? You taste some salt water. You go somewhere else along the beach. It tastes the same, right? Salt water all through it. Same throughout. So salt water. What about Kool-Aid?
It's the same.
Same throughout, right? What about salad?
It's different.
Different throughout, right? Heterogeneous? Any types of salad or casseroles, right? What about steel? Is it a pure substance, homogeneous mixture, heterogeneous mixture? Can you find steel on the periodic table? No, it's a combination of what? Iron, nickel, carbon, okay? And if it's stainless steel, maybe chromium, I think. I could be off. So steel is a mixture because we can separate it, right? So most metals that we have are alloys or mixtures of metals, okay? And how you do it is you just melt them together. Can you take them apart? Yeah, they have different melting points. So you melt it at a certain temperature, one of them falls off, right? And you're left with the other one, okay? So steel, another one is brass, okay? What about
Would that be hetero?
homogeneous? Because if you cut a piece of steel, it looks the same all the way through it, okay? What about concrete? Heterogeneous. On the outside, it looks homogeneous, looks pretty consistent. But if you've ever poured it or broke it apart, you can see there's chunks of rocks in there, right? What?
It's called aggregate.
Aggregate, yeah. Okay, good. Okay, so concrete. Granite, same idea, right? You have a granite countertop, it's not the same throughout. Different amounts of black part over here, more white part over here, whatever, right? What about air? Stuff we breathe.
Hetero.
Heterogeneous? Homogeneous? Pure substance? What do you think?
Heterogeneous.
Why?
Because we have bad air days.
We have bad air days.
And then days
Okay, let me ask you this, what about Kool-Aid? So you have Kool-Aid, and when you're younger, you have your brother or sister make some Kool-Aid, and it tastes nasty, right? They didn't put enough sugar in, or they put too much Kool-Aid in it, or not enough water, or something, right? But does that make it not homogeneous? Could it still be the same throughout? Okay, we have a good day in the air, and we have bad day in the air. Bad day, is it the same throughout? Yeah, it's just the same icky, right? And a good day, the same good. Well, think about it like this. Do we ever come over here in a corner, deep corner over here, and go, I can't breathe, I can't breathe, I can't breathe. That's better, right? You ever do that? I never have. What?
Just go up in altitude.
Well, if you go up in altitude, yeah, it's different there than it is here, and it might be different here than it is in a different state. But each place is pretty homogeneous. Does that make sense? So air would be considered homogeneous. Great discussion on that. I hope that. Do you have anything else to say? Maybe you could teach me something, right? All right. So don't be afraid to challenge what I say. Okay? Don't just believe me. Great, I love that. Anything else? Oh, let's see. What about blood? That's a little bit sketchy. But it turns out it's heterogeneous. Think about raw milk. You guys ever had raw milk? Go to your aunt's farm and they have right from the cow and they set it on the counter and what happens? It goes bad, right? You got to be careful because it might make you go bad. No, I'm just teasing. But the cream rises to the top, right? And it does it all by itself. And yeah, that's kind of how we know it's heterogeneous. But you get store-bought milk, and sometimes it has a sticker on it that says homogenized, right? Because it's the same throughout, always. And you can shake up raw milk, and then it's okay. You get about the same, okay? But it doesn't stay that way. Good? Any other questions about mixtures? Homogeneous, heterogeneous? All right. I think. Oh, we got one more thing to talk about here. Okay, so a mixture, we can separate it physically, right? So let's talk about how that's done. How to separate mixtures. And this is the last idea we'll talk about tonight. So next week we're probably going to spend the full time, all right? Just kind of getting our feet wet here. You guys okay with that?
Yes, sir.
Okay, you don't want to stay till 9 o'clock? Okay. All right. One way to separate is by filtration. Okay, you ever have spaghetti? You cook the noodles in water, and you take the water off by straining it, right? Through a colander. So what physical property do we use for filtration? Size. Is that what you said? Okay, yeah, size. The noodles have bigger size than the water, right? Or coffee, right? You put ground up coffee and then the water goes through it. Have the filter paper, right? Or painter's mask so that you don't breathe in the paint, but you can still breathe, right? Because the paint's larger particles and so on. Are we good with filtration? Another one is distillation. Anybody know what this is? You ever heard of distilled water? Or distilled alcohol? Right, you have the distillers that get you different, whatever, right? Make it more pure. Back in the day, that their moonshine and whatever, right? But how is it? What's the physical property that helps us to distill things? Boiling point, yeah. So difference in boiling points. So I'm gonna attempt to draw this, and this is what you might see in a chemistry lab. I mean, it's probably not exactly what it looks like if you go to an alcohol distiller, okay? But so we have our little burner here, and you have this flask. This comes down here, and it has this coil of tubes around it, and then that goes into this beaker and fills there, right? So what happens is you heat it, it boils, the water comes out, goes through this here, comes up here as steam. This part right here, you have cool water going through it, cools it down, and the water goes back in here. And what's left here is all the junk, right? So you got pure H2O. You ever taste distilled water? There's not much of a taste to it, right? Because it's just water. Most water we drink has stuff in it, right? Like whether it's spring water, has minerals and stuff in it, different taste. And we always get used to the water that we drink. It's like, oh, that's good water. You go to someone else's house, like, ugh, whatever, right? Okay. Any questions about distillation? Okay, what about using a centrifuge? What is that? You guys ever used a centrifuge? Yeah, it spins it around just like the amusement park rides, right? It spins you around, what does it do to you? Throws you on the outside, is that right? So what it does, it throws, so you have this little thing here with all these tubes, and they're kind of facing out a little bit, right? So you got this tube going out there, and this is kind of a top view, or whatever, and it pushes the more dense material on the outside, and then you got the less dense material on the inside, right? So that's the difference in density. Good? There's other types, but that's probably good enough. Good? But again, if we can separate it with differences in physical properties, it's a mixture. Good? Any questions? Was that too fast? Too dense? Okay? Perfect. Okay? Anybody do the reading before tonight? It really will. Does it help? Do it. Highly recommend it. Right now, we're in the basic stuff. We're going to get into more complex stuff. If you have the habit of reading your book before you come to class, you're going to have questions. When you have it in class, it's going to solidify in your brain better. And then afterwards, within 24 hours, review it again. And do some homework on mastering chemistry. Okay? We good? All right. Thank you very much. Have a great day. Have a great night, and drive safe, please.
Thank you.
Thank you.
Class start at 5 to 7 or 7 to 9. Like Tuesday, What time start?
I know, I always.
So-
On Thursday.
And so now I have to-
Both the same.
I
I
screwed
have
up.
2 classes.
I need this one. I need
You're in that one.
Tuesday and Thursday, I need from 7 to 9,
Mhm.
just the time. The okay, I dropped myself from yours.
Did you get in that one?
I couldn't, they put me in wait list, I don't know why. It doesn't matter the teacher, but the time very important. I'm working in the morning, I have lab,
Okay, if you need me to
please
try
just help
something,
me.
yeah.
I don't know what I do, I tried to register again tonight, just this time,
Uh-huh.
that's what is it. If not, I will send you a message or
Okay,
to help me.
yeah,
Thank you.
you bet. Yeah, do you have a question? What's your name?
Gene,
Gene?
yes, sir.
Nice to meet you.
Tuesday I worked night shifts in the
Okay.
nursery room and I was working, what's, y'all's attendance policy?
It's, make sure you come so you don't get too far behind.
Okay. I have, like-
I'm not gonna dog it down.
Okay, I have one more week, where I'm working Sunday, Monday, Tuesdays nights, so I might not be able to make next Tuesday as well.
Okay, I just recorded this.